This presentation is part of the TI-Nfocus AP Calculus video series. In this video, I'll discuss some technology solutions and problem extensions for the 2018 AP Calculus exam, free response question AB3 BC3. My name is Steve Kokoska. I'm a professor at Bloomsburg University of Pennsylvania, and I'm a former AP Calculus chief reader. Here's an outline of the information presented in this video. I'll start by reviewing the free response question, and then the scoring guidelines used at the AP Calculus reading. And I'll focus on the solutions presented in these guidelines, not how the points were awarded. Now, even though this question was not calculator active, I'll show you how to use technology to explore and answer parts of this question and to confirm solutions where appropriate. And because the free response questions are usually very comprehensive, I'll suggest some problem extensions, additional AP Calculus type questions associated with the information given in the problem. And some of these questions may be calculator active. This problem involved the graph of a continuous function g, the derivative of the function f. And the graph of g is given. In part A, we're given an initial condition, and we need to find f of minus 5. In part B, we need to evaluate a definite integral. In part C, we are asked to find the open intervals on which the graph of f is both increasing and concave up. And in part D, we need to find the x-coordinate of each point of inflection on the graph of f. Part A was worth 2 points. A common method to solve this problem involved the fundamental theorem of calculus, or the net change theorem. And so there was 1 point for writing the correct definite integral used in obtaining the answer, and 1 point for the final answer. Part B was worth 3 points. 1 point for recognizing and communicating that in order to evaluate this definite integral, we need to split it into 2 parts at x equals 3. There was 1 point for the antiderivative of the polynomial piece, and 1 point for the final answer, 10. Part C was worth 2 points. The student had to analyze the graph of g, the derivative of f, to answer this question. And the first point was for writing both correct intervals. The second point was earned for providing a sufficient reason for choosing these 2 intervals. Part D was worth 2 points, and once again the student had to use the graph of g to answer this question. The first point was for presenting simply x equals 4, and the second point was for providing a sufficient reason. One method to solve Part A involves the fundamental theorem of calculus. Since g is the derivative of f, we can write the integral from minus 5 to 1 of g of x dx is equal to f of 1 minus f of minus 5. Now, solve for f of minus 5. F of 1 is given in the problem. And to find the value of the integral, we need to interpret this definite integral as the area under the curve. From minus 5 to 1, we have the area of a square, a triangle, and another triangle. And we need to attach a negative sign to the area if the region is below the x-axis. The final answer here is 25 divided by 2. This is the equation given on the scoring guidelines, and some call this an application of the net change theorem. Notice that in this step, we make use of a property of integrals. This may be overuse of technology, but it's pretty cool that we can verify our analytical solution using the TI-Nspire. First, I defined the function g in pieces, and I had to derive all of those piecewise equations, well, except the last piece, which was given. I constructed a graph of g just to confirm my definition, and then I simply evaluated the expression as shown on the previous slide. Here's a nice extension to this problem. Let's work with the same function g, its graph, and again assume that g is the derivative of f. Now, we already know two values of the function f. However, in part A, find all these additional values of f. In B, plot all these values and use these points to sketch a rough graph of f. In part C, you might consider plotting f and g on the same coordinate axes, and then explain the relationship between these two graphs. And in part D, try to find an analytical piecewise definition for the function f. In part B, we need to find the definite integral from 1 to 6 of g of x dx. Now, because the definition of g changes over this interval, we need to split the integral into two parts, at the value where g changes. So we first split the integral at x equals 3. Then we can use the definition of the function g on each subinterval. The first integral represents the area of a square. So we can evaluate this using geometry or by using the fundamental theorem of calculus. However, we do need to find a symbolic antiderivative for the second integral. Now, many students can just look at this and recognize the u substitution and the antiderivative, and that's okay. But it's also fine to present a detailed u substitution on the AP Calculus exam. Here's the antiderivative. Then we evaluate at x equals 6 and x equals 3 and subtract. And put it all together. Here's the final answer, 10. Here's how I can use technology to solve this problem and to visualize the result. Now, I've already defined the function g, so I can simply compute the definite integral. The calculator knows how to deal with piecewise defined functions and returns the answer, 10. Now, in this example, the definite integral represents the area under the graph of g. So here's a graph of g with the appropriate shaded region. And the TI-Nspire computed the area of this region on the graphs page and also returned a 10, thank goodness. In part C, I'm going to show you another approach to solving this problem. And this will lead to, I think, a good question about concavity and points of inflection, and to the content presentation on this topic. So using the graph of g, I first constructed a sign chart for f prime equal g. I placed tick marks at the important values, where the derivative is 0 or does not exist. -1, 0, and 4. Now, this is an interesting problem because the derivative is 0 over an entire interval between -1 and 0. So I indicated the sign of f prime in the intervals and placed a 0 in the interval between -1 and 0. The sign chart indicates the interval on which f is increasing, 0 to 6. Then I used the graph of g to construct a sign chart for f double prime. The tick marks are at values where the second derivative is 0 or does not exist. Using the graph of g, I placed an appropriate sign in each interval. And this tells me where the graph of f is concave up or concave down. The graph of f is concave up on the intervals 0 to 1 and 4 to 6. Using these charts, I can see that the graph of f is increasing and concave up on the intervals 0 to 1 and 4 to 6. Remember, however, on the AP Calculus exam, a sign chart alone is not sufficient justification. So for full credit on the exam, I'd have to interpret these charts with a sentence similar to the one given on the scoring guidelines. Now, notice that I've placed question marks in 3 intervals on the second sign chart. I'll leave this as an open question. Discuss the concavity of the graph of f on these intervals, in particular on the interval 1 to 3. And I'll give you a hint. I think you need to consider the definition of concavity. And a graph later on in this video may help. I can also use technology to visualize this result. Here's the definition of the function f. Remember that f of 1 equals 3 is given in the problem, And here's a graph of the function f. It's a little tough to actually see the concavity here, but this does confirm our analytical results. The graph of f is increasing and concave up on the intervals 0 to 1 and 4 to 6. In part D, we need to find the x-coordinate of each point of inflection. Well, I can use the sign chart just constructed to find those values where there is a change in concavity. And there is only one x-coordinate, x equal 4. So the graph of f has a point of inflection at x equal 4 because f prime of x equal g of x changes sign from decreasing to increasing at x equal 4, or because the sign of f double prime changes from negative to positive at x equal 4. I believe my sign chart also verifies that there is no other point of inflection. And here's kind of a cool visualization of this result. First, I zoomed in near the point of inflection, and admittedly, it's still a little tough to see the change in concavity. So I constructed two tangent lines to the graph of f, one on either side of x equal 4. Using the definition of concavity, the tangent lines suggest that the graph of f is concave down to the left of 4 and concave up to the right of 4, and hence there's a point of inflection at x equal 4. Here's one more example for you to think about, or maybe even use in class. The graph of the derivative of a continuous function f is shown in this figure. Use this graph to determine the following. On what intervals is f increasing or decreasing? At what values of x does f have a local maximum? How about a local minimum? On what intervals is f concave up or concave down? And find the x-coordinates of the inflection points. And finally, let's assume that f of 0 is equal to 0 and sketch a graph of f. I hope this video gives you some good ideas for additional practice AP Calculus exam type questions, and of how to use technology to solve some of the parts of this problem and to explore, confirm, and visualize results. This problem in particular presents some good opportunities to discuss and really understand concavity and points of inflection. And just a reminder, there are lots of valuable resources on the TI website. There's material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.